Now here we can see very easily that these two to be analytic is that this value must not be 0. When this 0 is not defined, when 0 is not defined. So we say here the condition is a2 of x must not be equal to 0. So this is my leading entry. So I focus on this one and I say this must not be equal to 0. If at the point x equal to x0, when a2 of x 0 is not equal to 0, then we say x equal to x0 is ordinary point. Is ordinary point. So this is here number 1. Number 2, opposite to ordinary point is singular point. Singular point. The singular point will be opposite to this one. We say x equal to x0 is singular point. Singular point if we are having here a2 of x0 is equal to 0. We can find this, we can define the solution of the function about the ordinary point, about this point. But you can't define the function at the moment. I'm not going to discuss in further advanced level of method that we can have the singular points in terms of regular singular points and irregular singular points. Then we say regular singular point will define a method, we can find the solution. But in principle, we can define the solution about the ordinary point. So as we having here this x equal to, we have defined this series about the point x equal to x0 is ordinary point. We can define the series about ordinary point. So our solution, we can have an ordinary point, and obviously this ordinary point is about our ordinary point. When say here x equal to x0, this means we are having here the x0 mean absolute value of x0 is less than 0. This is the interval from minus infinity to infinity, including point x is around point x equal to 0. Around point x equal to 0, we can define our solution. So, so this was idea which I have discussed. This was number 1. We have discussed the series about x equal to 0 and its derivative. Then we have discussed here the ordinary points and the singular points. These singular points, and as I said, we can define the solution of the series about the ordinary point. And these are the two things. Then we are having the series which we call this Taylor series or Maclaurin series, and this series are defined about x equal to 0. I just give you the idea of that one. Take as a note. Important power series. We call this series as Maclaurin series. Maclaurin series, when we are having this defined at the point x equal to 0, otherwise we call them the Taylor series. So I am having here the series here e to power x. E to power x is 1 plus x squared by 2 factorial plus x3 by 3 factorial and plus so on. Then we have the sine function, sine of x is equal to x minus x cubed by 3 factorial plus x5 by 5 factorial minus plus so on. Then I have the cosine function, cosine of x is 1 minus x squared by 2 factorial plus x4 by 4 factorial minus plus so on. They are the series. We're having here one function, one having here ln of x. Now the series is 1 plus ln of x, 1 plus ln of 1 plus x. We can write in terms of series, we're having x minus x squared by 2 factorial plus x3 by 3 factorial minus x4 by 4 factorial minus plus so on. So these are some of the series we're having here. These all series are convergent about the point x equal to 0. Divergent other than that. So we can see here this is equal to enough for all these series. We're having these three series. This one, absolute value of x is less than 0. And for the series which is we're having the ln series, the x is between minus 1 and 1. So these are the domain on which the series are being defined. They are analytic. It means we can differentiate them, we can integrate them, and they are defined at the point. So we'll be going to use this one also. This is an idea you have to keep in mind. Three things again we have done here. We have find the series about they are analytic about x equal to 0. We can have this y dash, y double dash. And the series we can write in journal when take x equal to x0, power series when x is equal to 0, so we get here this series. Then we're having these two important ideas, that is the ordinary point and the singular point. We take here this differential equation in the standard form, and then we normalize this one. We divide by a2 of x. Then we say this p of x is a1 of x over a2 of x, q of x is a0 of x. These are analytic only when a2 of x is not equal to 0. So we have the condition that this value must not be 0. When we write this series, we write with this one that a2 of x is not equal to 0. When a2 of x is 0, then the structure of the series will change. So then we are having, when we say the point at which this a2 of x is not equal to 0, we call the point as ordinary point. And then we are having here the point where this is equal to 0. Then we say this point is a singular point. So other than this point, all points are ordinary points. At this point, if we find a point which is a singular point, then we say any other point will be a non-singular point. I give you some more detail about the ordinary point and the singular point. I take some examples for explaining this one, because we are going to use these ordinary points for writing our power series. Obviously, I have told you that we are going to use mostly, if possible, the series about x equal to 0 when x equal to 0 is an ordinary point. I can take an example, and we are having here example 1. Example 1. We are having this differential equation. Find the singular and ordinary points. Singular and ordinary and singular and ordinary points. The differential equation is x square minus 1 y double dash plus 2xy dash plus 6y equal to 0. Now we can see it here. My a2 of x is equal to x square minus 1. I factorize this one, I get a x minus 1 into x plus 1. We say which are singular points. Singular points are where we are having here a2 of x is equal to 0. This implies we are having x minus 1 into x plus 1 equal to 0. This gives me two values, x equal to 1 and x equal to minus 1. So x equal to 1 and x equal to minus 1, x equal to 1 and x equal to minus 1 are singular points. So we can see that this a2 of x is 0 only about the point here, these 2 points. Now is ordinary points. Ordinary points are the points where a2 of x is not equal to 0. So we can see here our a2 of x is not equal to 0 on the interval r, and we are having these 2 points out, it's minus 1 and 1. This is all the points in the interval r. When x is in this interval, they are set of the ordinary points. So if we look on this equation and say here a special case, note, here we can say x equal to 0 is ordinary point. OP means ordinary point, because when we're having x equal to 0, this is not equal to 0, it's equal to minus 1. So we can say if we're having a point x equal to 0 as ordinary point, our solution, we're going to discuss about that point.